Welcome to today's paper reading. Today's paper is titled, Scaling Synthetic Data Creation with 1 Billion Personas. This paper was published on the AR14 preprint by Haitao Ge and colleagues from Tencent AI Labs, Seattle. The authors propose a new method for data synthesis that uses large language models to generate diverse synthetic data by incorporating various perspectives. They introduce Persona Hub, a collection of 1 billion personas automatically curated from web data, which can be used to create diverse synthetic data at scale. The methodology is demonstrated through use cases in synthesizing high-quality mathematical and logical reasoning problems, as well as knowledge-rich texts, showcasing its versatility and scalability. Figure 1 illustrates how personas can be utilized with various data synthesis prompts to guide a large language model, LLM, in creating synthetic data from different perspectives. The Persona Hub, containing 1 billion diverse personas, enables the synthesis of various data scenarios at a massive scale. This approach leverages the unique perspectives of each persona to generate distinctive synthetic data, showcasing the versatility and scalability of persona-driven data synthesis. The introduction of the paper discusses the growing importance of synthetic data, which is data generated by models or algorithms rather than directly by humans. This type of data is increasingly valued for training large language models, LLMs. However, creating synthetic data at scale is challenging because while it's easy to increase the quantity, ensuring diversity is difficult. The paper highlights the need for diverse prompts to create diverse synthetic data. Previous research has attempted to diversify data synthesis prompts through instance-driven and key-point-driven approaches, but these methods have limitations in scalability. To address these challenges, the authors propose a novel persona-driven data synthesis methodology. This approach is inspired by the observation that adding a persona to a data synthesis prompt can steer the LLM towards creating distinctive synthetic data. The methodology is scalable through the construction of a comprehensive persona collection, known as Persona Hub, which contains 1 billion diverse personas. This approach is versatile and can be applied to various data synthesis scenarios, potentially driving a paradigm shift in synthetic data creation and applications. Figure 2 illustrates the concept of Persona Hub as a compression mechanism for world knowledge. It shows that Persona Hub, containing approximately 10 billion tokens, can be viewed as a compressed form of the vast world knowledge available in public web text, which amounts to about 100 trillion tokens. This compression is achieved by representing the world knowledge through diverse personas, each carrying a unique perspective and set of experiences. Conversely, the public web text can be seen as the decompressed content generated by these personas, reflecting their collective knowledge and experiences. This perspective highlights how Persona Hub serves as a distributed carrier of compressed world knowledge, offering a scalable and efficient way to represent and access vast amounts of information. Figure 3 illustrates the text-to-persona approach, which leverages any text as input to derive corresponding personas. This is achieved by prompting the large language model, LLM, with the question who is likely to read, write, like, dislike, the text? This method allows for the extraction of personas based on the content of the text, providing a versatile tool for persona-driven data synthesis. Figure 4 illustrates how the granularity of persona descriptions is influenced by the detailed elements present in the input texts. When texts, such as those from mathematical textbooks or academic papers on superconductivity, contain numerous detailed elements, the resulting persona descriptions become more specific and fine-grained. This demonstrates the capability of the text-to-persona approach to generate detailed personas based on the complexity and specificity of the input text. Figure 5 illustrates how persona-to-persona method derives diverse personas through interpersonal relationships. This is achieved by prompting the large language model, LLM, with questions like who is in close relationship with the given persona. For instance, a child persona can be derived from a nurse persona, and a beggar persona from a shelter worker persona. The process involves 6 iterations of relationship expansion for each persona obtained through text-to-persona, thereby significantly enriching the persona collection. Figure 6 illustrates 3 methods for prompting data synthesis using personas. The zero-shot method relies solely on the model's creativity without any examples. Few-shot prompting enhances data synthesis by including demonstrations. Persona-enhanced few-shot prompting further improves synthesis by integrating personas, though it necessitates deriving personas for each demonstration. Figure 7 illustrates the application of a linguist persona in generating math problems with specified focuses such as geometry or Olympiad-level difficulty. This approach demonstrates how personas can be utilized to tailor math problems to specific contexts and challenge levels, enhancing both the relevance and the complexity of the problems created. Figure 8 presents examples of math problems generated using personas of professionals in the field of mathematics. These problems are notably more challenging than those created with general personas, as they demand a deeper and more detailed understanding of advanced mathematical knowledge and skills. This approach highlights the complexity and specificity required by professionals in the field, showcasing the difference in difficulty levels when compared to problems designed for a broader audience. Table 1 showcases the in-distribution evaluation results on the 11.6K synthetic test instances. Among the open-source large language models, LLMs, Qwen2-72b Instruct performs the best, followed by other models generally consistent with their performance on other mathematical benchmarks. Notably, the Qwen2-7b model, fine-tuned with 1.07m synthetic math problems, achieves nearly 80% accuracy, surpassing all other open-source LLMs. However, due to potential reliability issues with the synthetic test set answers and the unique use of in-distribution training data by our model, these results should be interpreted with caution. Table 2 presents the out-of-distribution evaluation results on the math dataset. The model fine-tuned with 1.07m synthetic math problems achieves 64.9% accuracy, which is comparable to the performance of GPT-4 Turbo Preview at a significantly smaller scale of 7b parameters. Results marked with an asterisk symbol, indicate that they may not have used OpenAI's evaluation method. Figure 9 illustrates the accuracy of the Qwen2-7b model on the math dataset as the scale of synthetic training instances increases. The model's performance generally follows the scaling law, demonstrating that synthetic data can effectively train the model without relying on in-distribution data from math. This out-of-distribution evaluation shows that the 7b model can achieve performance surpassing GPT-4 Turbo Preview, which is a significant achievement for a model of this size. Figure 10 illustrates the relationship between the semantic similarity of personas and the math problems they generate. Part A shows the similarity without specific prompt constraints, Part B with constraints related to finance and probability, and Part C compares the synthesis by GPT-4o and GPT-35 Turbo using highly similar personas. The results indicate that while problem similarity tends to follow persona similarity, it is generally lower, especially when more specific constraints are applied. The comparison between GPT-4o and GPT-35 Turbo shows that their generated problem similarities are not significantly different, suggesting that persona-driven synthesis can maintain diversity even at large scales. Figure 11 showcases examples of logical reasoning problems synthesized using our proposed persona-driven methodology. These problems demonstrate diversity and high relevance to the personas, illustrating the effectiveness of our approach in generating varied and persona-specific logical reasoning challenges. Figure 12 illustrates Roseba-style logical reasoning problems generated using various personas. It highlights that logical prompt 3 is presented in a simplified form for clarity. In actual practice, a precise definition of a Roseba-style logical reasoning problem is required within the prompt to produce the desired synthetic data. Figure 13 illustrates two methods for synthesizing user instructions: zero-shot prompting and persona-enhanced few-shot prompting. The zero-shot method generates instructions without relying on existing datasets, while the persona-enhanced few-shot method uses existing datasets like WildChat to create more realistic instructions. This figure highlights the text-to-persona method for inferring personas, which enhances the complexity and realism of synthesized instructions. In this section, we explore the methodology of training and post-training of large language models, LLMs, using Persona Hub. By prompting LLMs with personas sampled from Persona Hub, we can elicit highly informative and knowledge-rich content. This approach scales effectively with the 1 billion personas available in Persona Hub, covering a vast array of topics. Additionally, we discussed the application of Persona Hub in creating diverse non-player characters, NPCs, for games. By projecting real-world personas into game characters, we significantly reduced the effort required for brainstorming NPCs during game design. Furthermore, we introduced the development of tools using Persona Hub. By predicting the tools users might need, we can pre-build these tools, allowing LLMs to directly call them when needed, thus expanding the range of services provided by LLMs. Figure 14 demonstrates the synthesis of knowledge-rich plain text using personas. The process involves prompting an LLM to write Quora articles based on personas sampled from Persona Hub. This method leverages the LLM's knowledge and perspective, resulting in informative content. By scaling with 1 billion personas, a vast array of knowledge-rich text can be generated covering diverse topics. Figure 15 illustrates the process of creating non-player characters, NPCs, for the game World of Warcraft using personas from Persona Hub. The example NPCs include Lyria Moonwhisper, a night elf druid with a background as a nomadic photographer, and Mei Lin, a Pandaren chef who is a restaurant owner. These NPCs offer unique quests and interactions that reflect their real-world personas, enhancing the game's immersive experience. Figure 16 illustrates the process of creating NPCs for the game Moonlight Blade, using the Persona Hub. This figure showcases how Persona Hub is integrated into the game development process to generate unique and engaging NPCs, enhancing the player experience within the game world. Figure 17 illustrates examples of tools created using various personas within Persona Hub. These tools are designed to fulfill functionalities that specific personas may require, such as a cab driver needing to check traffic conditions, which an LLM cannot directly access. This expansion of services provided by the LLM is significant. Although the tools in Figure 17 are initially defined as interfaces, they can be easily converted into functional code implementations, as demonstrated in Figure 18. This approach allows the LLM to utilize pre-built tools directly, eliminating the need for repetitive tool creation from scratch. Figure 18 illustrates the conversion of interface definitions, such as the species identification interface, from Figure 17 into actual code implementations. This process demonstrates how abstract interface definitions can be concretely realized in programming, showcasing the practical application of these definitions in software development. In this section, the authors discuss the effectiveness of their methodology in scaling synthetic data creation across various scenarios. They highlight its potential to revolutionize the creation and application of synthetic data, positioning it as a general data synthesis engine for both research and practice. The current version of Persona Hub, containing 1 billion personas, is noted for its lack of fine-grained details. Future versions aim to refine these personas to be as detailed as Wikipedia articles, enhancing uniqueness and scaling opportunities. Additionally, the authors plan to explore the application of their methodology to multimodal LLMs and the use of super personas to guide LLMs beyond existing knowledge, potentially unlocking new approaches to accessing superintelligence. In this section, we review several key areas of related work. Firstly, instruction tuning for language models, as detailed in AR14, 2402.13064, focuses on the steerability of large language models toward data-driven personas. Secondly, the use of synthetic data for language models is discussed in AR14, 2404.07503, where best practices and lessons learned are highlighted. Lastly, the dynamic LLM agent network, described in AR14, 2310.02170, presents an LLM agent collaboration framework with a focus on agent team optimization. In this study, the authors introduce MathCoder, a novel approach that seamlessly integrates code into large language models, LLMs, to enhance their mathematical capabilities. This integration is shown to significantly improve the performance of LLMs. The research is based on scaling with human-generated data, as presented at the 41st International Conference on Machine Learning in 2024. Authored by Wang, Huing Ren, Aojuan Zhou, and others, this work not only presents a new method for LLMs but also opens up potential avenues for future applications in mathematical problem solving. Thank you for watching.